So we looked at the vocabulary of transformations. So we have a basis of positive frequency modes, two different bases, two different complete sets of homogeneous solutions of the Klein-Gordon equation. You write the field in terms of this, and what we find is that the creation of the annihilation operator with respect to one of them contains an annihilation operator with respect to the other one, but also creation operators with respect to the other one. If beta is different from 0, that tells you that annihilating one vacuum state is not going to be equivalent to annihilating the other vacuum state, but it is also going to create some particles as well. The two vacuum states are not going to be the same if one of these beta coefficients is different from 0. So we're started looking at the consequence of this, which is the Unruh effect. And I think I didn't do the Penrose diagram yet. But we've got a uniformly accelerating observer, which is called a linear observer. In 2D, is in 2D flat spacetime. And the coordinates that we use, well, you can write it in null coordinates, and I also introduced the linear coordinates. So the linear coordinates are eta and zeta. So eta and zeta defined in this way. For some constant value of alpha. And we saw as well that the acceleration, so this is a uniformly accelerated observer with acceleration given by alpha exponential of minus alpha zeta. So this corresponds to zeta equals constant. This is a linear observer. And writing the line element in terms of this, that gives you this form. And so the proper time of this guy is, we call it top, and then just the square root of minus this thing, because z equals constant gives you the linear observer. Okay, so let's play around a little bit more with this. So first of all, t over y, that gives you the tangent of alpha eta, because the tangent goes from -1 to +1. So I already wrote this down all this last week. And y so this is eta and zeta. For eta and zeta, going over the all real numbers, that gives you these regimes for t and y. Okay? So note that it only covers positive y. So all real z times zeta does not cover the full flat space time. It only covers a patch of it. So this guy is covered only y larger than t, because if this is t over y is between -1 and 1, that means that t is between -1 and plus y, -1 and plus y, and this is 1/4 of flat space-time, and it's called the right Riemann wedge. So it's a Riemann wedge. Okay, so this is like in Schwarzschild coordinates. Schwarzschild coordinates only cover outside the black hole space-time. You need another set of coordinates to cover the full space-time, to go inside the black hole and cover the full space-time. So this is similar. This pair of coordinates, whenever they range over the whole real values, they don't cover the full flat space-time. It's an issue, if you wish, with the coordinates. You can define another set of coordinates, defined in a different way in terms of t and y, that cover another part of the flat space-time. So we can obtain a second, now I'll call it left L, and this will be right, or left Riemann wedge, by another set of coordinates, so another eta and zeta defined in a different way, even though I use the same symbols, they're defined in a different way in terms of t and y. So this is minus sign now, exponential alpha, zeta, alpha, shine, alpha, eta. And similarly, y is now minus the same thing, alpha, zeta, alpha, cosh, alpha. Okay, and now y, so again, eta and zeta defined in this way, whenever they go over all the real numbers, that gives you that y is negative, and again t goes between -1 and +1. So we've got another Riemann wedge. So that's y between t between y and -y. Okay, now y is negative, so obviously this is positive and this is negative. So let's do a diagram of these wedges. First of all, we'll do a standard ty diagram. Okay, this is still not a Penrose diagram. Okay, so t equals y is the null cone going through the origin. T equals y, and this is t equals -1. T equals y corresponds to u equals 0, and to z equals -infinity, it equals infinity. So you can see this in many different ways. One is, for example, I wrote down minus t squared plus y squared equals alpha zeta alpha squared. If t is equal to y, if t is equal to plus minus y, we need zeta to go to minus infinity. So that tells you that zeta should be that. And t equals minus y, that's also zeta, that's v equals 0, zeta equals minus infinity, and e equals minus infinity. Okay, t equals y. From here you can tell that's equal to 1, and so you need eta to go to plus infinity. Eta equals minus y, you've got the tangent of alpha eta to be equal to minus 1, and so you need eta to be minus infinity. Okay, now these are the UV planes. So this is this V equals 0. So V runs around this way. So and U runs this way. So this is V positive, V negative, U positive, U negative. The Z equals constant, they're hyperbola, okay, where Z equals constant means minus t squared plus y squared equals constant, that's a hyperbola. So you've got hyperbola that asymptote to t equals y and t equals minus y. So this is zeta equals constant. And of course you've got, depending on the values of alpha and zeta, you'll get different hyperbola. And that's valid, that's true from the left and from the right. Okay, which region is the right Greenland wedge? Yeah. So this region here, this is R, or Y larger than absolute value of t. Y equals absolute value of t would be equal to this. If y is larger, then it's inside that. The wedge, the left Greenland wedge is this right here. So this is the left Greenland wedge. Or I should say, you've got hyperbola going this way as well. This is zeta. This is also zeta equals constant. And this way. So we call this the future. Okay, this region, this wedge here is called the future, and this one is called the past, for obvious reasons. Or you can do, well, I didn't say what zeta is here, but you can do a similar coordinates, zeta and eta in P and F in the future and the past to cover the whole space-time. Okay, so you need 4 patches of zeta and eta coordinates in order to cover the full flat space-time. write again the metric. What are the given vectors for this metric?
At least one zeta is 1, 0.
What's the vector?
1, 0. If which
Which basis is this?
and the base is an eta key psi. I don't know the zeta.
So 1, 0 means you mean TD and then?
Yes.
Okay. Any other ones?
Ty infinity.
Right. So that's right. So the metric does not depend on these coordinates on t and theta. So these are our given vectors. Which ones are time-like? Which ones are space-like?
T time-like.
Time-like.
Eta time-like. And the one is space-like.
Okay. Which way does? What's the direction of TD then? Let's do it easier. What's the direction of DDT? Yeah. So DDT at any point goes like this. What is the direction of DDY? What's the direction of DD then? What does that mean?
Tangent to the hyperbola.
Sorry?
Tangent.
Tangent to the hyperbola, that's right. In which direction? Up or down? Up. In which direction, up or down? Up. What? Up. How many ups? One up.
How could you see that it was tangent to the hyperbola?
Is it direction of the whirling, right?
So is the direction that
What whirling?
Of the observer.
He's saying correctly, not very rigorously, but correct. The idea is that. It's the time. How do you know? Well, I can revert the question. You said that DDT goes like this. So how do you know DDT goes like this?
You just define the axis that way. You begin with.
But how do you know?
You could set up.
The reason why it's like this is because it's y equals constant. It's the other coordinate equals constant. This guy is the other coordinate zeta. Zeta equals constant. So that's the direction. So in here, is it up or is it down? We've got one up. Any downs?
I would go down just for.
Yeah, you always, you always vote.
Just keep the prophecy.
Okay.
I understood how to check the direction, but not the sentido.
Okay. How do you get this? Why is this DDT going up?
You define the axis, the t-axis would grow in that direction.
Okay. So how would say does eta grow when t grows, or does it decrease when t increases? So it's the value of eta. The z equals constant, but eta varies along here. Okay.
Okay.
So does it grow in this direction, or does it decrease in this direction?
It increases in that direction.
Why is that?
Because if you find t minus.
Exactly. So this is in the left wedge. So as eta increases, t is going to decrease and the way around. So in this part, dd eta goes down. In that part, dd eta goes up because, well, basically because there was a plus on the right wedge. So as eta t increased, eta increased as well. That's not the Penrose diagram. So, but now we know how to do the Penrose diagram with this. Penrose diagram. Penrose Carter diagram. Remember, we want to compactify. We want infinities now to have finite corresponding coordinates that have finite values. So we define little u as tangent capital U, so that now infinite values for little u and v correspond to finite values of capital U and v. Okay, so I already drew the Penrose diagram for flat spacetime, so it's just the same. By the way, some people call it Riemann space. I don't understand why people call it Riemann space. It's flat spacetime. We're just using a different set of coordinates. Okay, it's very commonly called Riemann spacetime. It's just flat spacetime. Okay, just using Riemann coordinates. So the Penrose diagram is just Penrose diagram of flat spacetime. It's not different. The line cone going through 0 are these diagonals, because we're just compactifying, we're not changing the causal structure. And so this region here is the left wedge, this region here is the right wedge, this is the future, and this is the past. And a reader observer will do this. Okay, so this is a z equals constant war line. It's the war line of a uniformly accelerated observer. Remember when I explained about Penrose diagrams that not all time-like war lines end up, and so this would be I plus, this would be I minus, this would be scribe plus right, scribe minus right, scribe plus left, scribe minus left, I0 left, I0 right. Not all time-like war lines end up at I plus. Geodesic time-like geodesics do end up at I plus. This war line here is a time-like war line. It's the war line of a massive observer. So it's a time-like war line, but it's not geodesic. It's accelerated. And it does not end up at I plus, it ends up at I plus. Because it's accelerated, so it's initially going with virtually infinite speed of light velocity towards the left, towards negative y, but the acceleration is towards the right. So the velocity keeps decreasing, until it reaches 0, and then it starts acquiring a positive velocity towards positive y, until it doesn't close to having a velocity equal to the speed of light in the positive direction. So that's what a Riemann observer is. And this is, like I said, is u equals 0, and this is v equals 0. Okay, and the killing vectors, so these are the killing vectors. Okay, because the metric is independent of these guys. Now, this is time length. Cassie said that this is time length. Do we all agree with this?
I would have to write it with the derivatives to find out what is the relation between d eta
But
the other one.
this is time. If this is negative, this is time length. This is the definition of time length. Okay. Psi equals, let's consider just this one. That's the interesting one. Is it 0 anywhere?
No. Scribe minus infinity?
Why is it not zero? Why is it not zero? What is this about? What is this equal to?
Of exponential of 2 alpha minus exponential of 2 alpha.
Exactly. So this is g alpha beta psi. So this will be psi alpha. Okay, these are the, this is psi, and so psi alpha is, in this case, let's do this properly. So psi equals d eta. This means that psi alpha is delta alpha eta. Okay. The only component that's not zero is the eta component. So psi squared is g alpha. Let's do it. G alpha beta psi alpha psi beta. Only the eta component matters. So this is just g eta eta, and it's like Hansen says, it's minus exponential of 2 alpha zeta. Can this be is this zero anywhere?
Can I see approach to 0 at infinities?
What infinities?
Is that
Zeta equals infinity?
Zeta equals infinity minus infinity.
Yes.
This will be exponentially, this will go to 0. And so psi squared is null. Psi squared is 0. And so psi, so d eta is null. So zeta equals minus infinity if t equals y and t equals minus y. So these two lines are zeta equals minus infinity. Okay. This is t equals plus minus y, or u equals 0 and or v equals 0. So these are called Keeling horizons. This is where a Keeling vector becomes null. different names for this. Well, there's different names for this. People use cosmological horizons. Some people use. I don't know. There's other names for this. Okay. This is probably the more rigorous way. But this has consequences. What does this mean? dd eta is the integral curves of dd eta are the word lines of a Wheeler observer, of a uniformly accelerated observer. Okay. The integral word lines of dd eta is this. The integral word lines of this are these hyperbola, which are the word lines of uniformly accelerated observers. So an accelerated observer following one of these lines is never going to receive anything coming from the left wedge. Anything coming from the left wedge, at most it will go light propagated 49 degrees, so it will go in this direction, but never, it will never be able to reach an observer here. Or from here, of course. Similarly, nothing that this observer emits will be able to reach L or P. It will reach anywhere in F and places in everywhere in R, but not nowhere in M. So there's a constant disconnection between these Wheeler observers and some parts, wedges in the spacetime. Okay, so no events in L or F can be observed by a Wheeler observer in R, and no events in L or P can be affected by a Wheeler observer in R. So L on R are constantly disconnected. Any questions? This that looks so obvious and naive has big consequences in QFT. This creates manipulation. When I say manipulation, I put that in quotes, of course, we'll never know my body. So there's a profound connection between the geometry and the QFT in many ways. So we're going to see this now in a second. Before we do that, let's express U and V in terms of eta and zeta. So U is t minus y, that gives you this. So that's 0 in the Wheeler wedge, and V is t plus y. Which is positive. This is in the Wheeler wedge, the right Wheeler wedge. And you can do a similar thing in the left Wheeler wedge. Okay, I already drew this in the diagram. U is negative. In R, U is negative, and V is positive. And the left inner wedge, V is positive, sorry, V is negative, and Q is positive. That's the way we draw it. So let's look at the classical field. So I'm going to keep this Penrose diagram. I want to leave it here. So let's look. So this is Brinner observer. This is the geometry. Now let's put a field of this. So conformally coupled scalar field, massless, and real. Now, in 2D, 1 plus 1D. So remember, conformally coupled means that the wave equation is related by in two different spacetimes related by some conformal factor in the field. That conformal factor, so the coupling constant, we call it psi n, and it's proportional to n minus 2, where n was the number of dimensions. So psi equals 2, conformally coupled means that we're taking psi equals 0. Okay? Conformally coupled means that we're taking psi to be equal to psi n, where psi n was the conformally coupled value for psi. For n equals to in 2 dimensions, that value is equal to 0. So we're taking conformal coupling constant equals 0. That means that the action is going to be formally the same in the two different coordinate systems. So the action for the field so I gave the expression CFT. This is just G mu derivatives phi. This is a scalar field, so the covariant derivatives are just you can replace them by partial derivatives. Now you can write this in the Ty frame and in the zeta eta frame. So the Ty frame square root of minus g is I'll write the line element here. So the square root of minus g is equal to 1 for in ty coordinates. G is the determinant of the metric. And then you just have this, so that's just going to be minus dt squared, dt, second partial derivative, dy. Okay. That's just the action for the, sorry, it's not second order derivative, but squared. Okay, so that's square root of the first order derivative. You can do the same in the eta and zeta coordinates. So in here, square root of g is just this times this and take the square root, so we just exponential of 2 alpha zeta. And then this guy would be g eta eta, so minus exponential of 2 alpha zeta. Sorry, this obviously is G covariant form. This is in covariant form. We want the contravariant form, so that's going to be its diagonal metric. So the inverse is just the inverse of each element in the diagonal. So that's going to be minus the inverse of this, and then just derivative with respect to eta, and then same thing for the other one, similar thing for the other one. And the exponentials go away here. So that this is formally exactly the same as in the other coordinates. So what does that mean? You want to get the Klein-Gordon equation from this. So you need to differentiate, the functional derivative of the action with respect to the field has to be equal to 0. The extremize of the field equation is extremize the action. And then formally it's going to have exactly the same equation whether you're using ty coordinates or eta and zeta coordinates. The Klein-Gordon equation, which is obtained by extremizing the action with respect to the field, is formally the same. In the two coordinate systems. I'm going to steal the left blackboard. Okay, so I'm going to do two columns. So T and Y. What's the Klein-Gordon equation? Is just equal to this. Now it is second order derivatives. And what is it going to be in eta and zeta coordinates? What?
The second derivative of
Minus the second derivative. So it's exactly, formally, it's exactly the same. The solutions we know what they are. We did it in 3+1, and the essentially the same things in in 1 plus 1. Okay. So let me write again u and v. So I just wrote down u and v in terms of beta and zeta. This is what I wrote down a second ago. So I want to write this in u and v. Okay, so k and omega. So omega is just absolute value of k. So k goes over the reals. Omega is just positive. Okay, so then it will be different whether k is positive or k is negative. Whenever k is positive, we're going to have exponential of minus I omega t. K will be, in the case that k is positive, k will be equal to omega, so plus I omega y. So that's just minus I omega t minus y. And t minus y is 0. This is for k, so for k positive. For k negative, we'll have expansion of minus I omega t minus I omega y. That's minus I omega t plus y, which is v. And so this exponential of minus I omega v. Well, I still, yeah, that's it. For k negative. So what, in which direction? So this is a wave that's propagating in the flat space-time. In which direction is it going?
Orthogonal to u.
Sorry?
Moves orthogonal to u.
So you're saying that exponential of minus I omega u goes in this direction?
Yes.
Any other ideas? Why do you think that?
The argument of the function is the t minus y line. So along this t minus y equals constant, the function will not change. It
Exactly.
will only change when you change the u equals constant line. So
Exactly.
it should be in u.
But that's not. The first part of the reason is correct, but the conclusion is not correct. Like to say if you look at the peak of a wave, so a wave is propagating in time like this. If you just look at the peak, okay, as you say, the peak is going to be at the u equals constant line. So the peak is going to be all the time here. So if you follow the peak with time, the peak will be here, 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 here. So that's the way this guy is propagating.
I see.
And in fact, this is an exact solution. It's flat space time. This is exactly this is an exact solution all the way from square minus to square plus. Similarly, exponential of minus I omega v will be this. What if we had exponential of plus I omega u? Which direction is this moving?
To move from the future to the past, I guess. In this direction, diagonal.
Like this.
So Cass is saying this way. Cass is saying this way.
Wait.
Joao says this way.
We have two more choices.
Any other suggestions?
So
U is t minus 1. As t increases, if you want to keep u constant, what does y have to do? Increases, right? So say you're here, as t increases, what does y have to do? It has to increase this way. U equals constant corresponds to this. And this is true regardless of this sign. So exponential of plus I omega u would also go exactly this way. It's irrelevant of the sign. You want to peak, you want to trace the maximum, and as t increases, y has to increase in a way that it follows the diagonal. Okay, so that's the ty solutions. Now, what about, I'm going to call them this. So I'm going to use, instead of k, I'm going to use k bar. Instead of phi, I'm going to use phi bar. R, because these are going to be in the right Wiener wedge. So formally they are the same. Okay, so formally they are 1 over square root of 4 pi omega bar, where now omega bar, so k bar goes over the reals, omega bar is just the absolute value of k bar, which is positive, of course. Formally it's exactly the same, so it's going to be exponential of minus I omega bar eta plus I k bar zeta. Just formally the same solution. So that's the same. So let's take split between k bar positive and k bar negative. Also, so this is, well, we're going to define, so this is in the right Wiener wedge. I'm going to define this to be 0 for x in the left as a function of x, for x in the left Wiener wedge. So for k bar positive, this is going to be exponential of alpha. Well, okay, we can write it like this. Okay, all I'm doing is, for k bar positive, omega bar is equal to k bar. You could use omega bar here if you wish. And I'm just multiplying and dividing by alpha. Okay, that's not doing anything. The reason why you do this is because I want to recover, in this case I want an alpha here to recover u. So this is minus alpha u. For k bar negative, we'll have alpha zeta plus zeta now. And because I multiply by alpha, I want to divide by alpha here. And this is for k bar negative. I include the alpha so that we have this thing here. So this is alpha v. So these are complete sets. So phi k form a complete set in the whole of the spacetime. Phi bar r k bar form a complete set in R. Any value of the field in R can be obtained via linear combination of this set of solutions. Obviously, in L, that can't be the case because they're just equal to 0. Their positive frequency with respect to ddt. If you take ddt phi k, you get minus I omega phi k with omega positive. Okay, that tells you it is positive frequency with respect to ddt. These guys, their positive frequency with respect to dd theta. Okay, dd theta times this, applied times this, is minus I omega bar, phi bar, rk bar, and their positive frequency is minus here, because omega bar is positive. This means that I have positive norm. Similarly here, we've got phi k bar r, phi bar r, k bar times also delta k bar minus k bar. Now, these guys, as I said, they are just concentrated on R. They're equal to 0. By definition, we're choosing them to be like this. They're equal to 0 to the left wedge. So if we need some other set of modes that mirror this for the left wedge instead of the right wedge. So I'll write them up here. So now we define phi bar L k bar as this. Again, you can split it between k bar positive and negative. So this is in L, and phi bar L K bar are positive frequency with respect to which vector. Sorry?
That again.
Sorry?
That again.
Eta? Did eta? Any other suggestions?
It is minus I omega bar eta.
Why minus?
No, I mean I'm missing. This is minus or no? This is not minus.
No.
So no, it's not. It's not.
So with respect to which vector are they positive frequency?
Minus.
Minus dd eta, exactly. So they are positive with respect to minus dd eta because now we've got minus I omega bar being positive. Okay, that makes sense. That's why we choose it like this, because this guy is future directed in the left wedge. Remember that dd eta was going towards past minus d eta. So in here, minus dd eta goes this way, minus dd eta goes towards the future, and so we find them to be positive frequency with respect to what is a future directed time-like vector in the left wedge. And we also, so there are, we also have this. Okay, so now we can, so far as classical field theory, now we can quantize. So you expand the quantized field in this way in terms of the Ty frame. So you can. It is usual to rewrite this in terms of a positive frequency, an integral over positive omega bar, omega. So you can rewrite this in terms of omega. And for positive omega, you just get the same. For negative omega, sorry, for negative k, you want to change the change the sign of omega. That's expansion. you impose the computation relations and the Minkowski vacuum is, like we know, it's the vacuum M such that it's annihilated by all these K's, AKs. And you do the same thing in the Wiener frame. So now we have to include the right modes and the right wedge modes and the left wedge modes. And impose the commutation relations both on the coefficients. These Fourier mode coefficients are called P. You've got BR, BL, depending on it goes with the right wedge solution or the left wedge solution. And these are creation, both of these are annihilation operators. So you can define a new vacuum which is annihilated by these two sets of annihilation operators. And it's called the Wiener vacuum. So, we define two vacuum states, or two quantum states. Are they the same? Are they physically the same? There's two quantum field theories related by a unitary transformation.
Well, happy to talk with the book about to see
Yeah, that's right. So let's do that. We're going to do it in the way. So you need to express these modes in terms of a linear combination of these modes and these modes. If the non-complex conjugate, so if the positive frequency modes here contain not only positive frequency, but also they need some negative frequencies with respect to ddt. Okay, these are positive frequency with respect to ddt, these are positive frequency, negative frequency with respect to ddt, these are positive frequency with respect to dd eta. If the positive frequency modes with respect to dd eta contain, you can express them as a linear combination of the phi k's and phi k stars. If they include any phi k stars, if they include any negative frequency modes with respect to ddt, then the vacuum that corresponds to these modes, the linear vacuum, is not going to be the same as the Minkowski vacuum, the vacuum with respect to ddt. Okay. Because those coefficients are the beta coefficients, the beta Bogoliubov coefficients that we saw, that's what gives rise to quantum particles in one state with respect to the other state. Okay, so the way we're going to do it, you can do this in different ways. We're going to do it in the smart way that Bill Unruh did it. So it's the matter of Unruh that's PRD Fujin 870, 1976. Okay, so the Minkowski modes, we call them Minkowski modes, phi k are analytic in the lower half U plane and V plane. U and V planes. They're also bounded in those planes. Okay, suppose so remember we had exponential of minus I omega u, exponential of minus I omega v. So when I say U plane and V plane, I'm talking about complex. We're complexifying U and V. You just let them be complex. Lower half, I mean negative imaginary U, negative, but negative imaginary V, negative. Okay? So suppose that U and V have got a real part and imaginary part. So that's exponential of minus I omega real part, exponential of omega U I part. Okay, so this is U equals a real part plus an imaginary part. If Ui is negative, you let it be infinitely negative, that's going to be bounded, that's going to go to 0. If Ui let it be positive, then that's unbounded to the upper plane. So they are analytic in the lower half and UV planes. In fact, they're analytic in the upper half of UV planes as well, but they are bounded. They're also bounded in the lower half U and V planes. They're not bounded in the upper half U and V planes. They grow without the bounds. This also means that any linear combination of phi k will also satisfy these properties. if you have a negative frequency mode, so these are positive frequency with respect to DT, if in the linear combination you include any negative frequency modes, they're not going to satisfy these properties. Okay, so you're going to change the sign of this. So you first complex conjugate them. So you would have an exponential of plus I omega u, and so you would change the sign here. That doesn't affect boundedness. You would change the sign here, and so that affects the fact that it wouldn't be bounded in the lower half u and v plane. Okay? So if any negative frequency mode phi k star were included in the linear combination, these properties would not be satisfied. So these properties are, so these are defining properties of positive frequency modes with respect to ddt. Okay, if you take any linear combination of positive frequency modes, you're still going to have a positive frequency mode. Any combination of phi k will also satisfy these properties, and obviously, and will be positive frequency mode with respect to ddt. You just put together all positive frequency modes, so the result will also be a positive frequency mode. If you include any negative frequency modes, the result will not be a positive frequency mode, and you won't satisfy these properties. We have a positive frequency mode. A positive frequency solution means that if you Fourier decompose it, you want that all those modes are satisfied and have positive frequency. Okay? But if you include in the linear combination any mode which is negative frequency, the result is not going to be a positive frequency mode. As long as you include one Fourier mode which is not doesn't have a positive frequency. Okay, that's the Minkowski modes. What about the Wheeler modes? Do they satisfy these properties? What about the Wheeler modes? Take, for example, the case k bar positive. It would just drive to the second ago. It's equal to this. For u negative, this is for x in the in the right Wheeler wedge or the left Wheeler wedge, for u positive, it means that we are in the right Wheeler wedge. Okay, this is u positive. So now we are u positive in the right, u positive in the right in here. So that's anywhere here. And in the left, we have 0. That's for u positive. in this case we're U positive, but we are only in R or L, and so U positive is a mode in the, gives you a point on the left river wedge. Now this is not analytic, it's something that is non-zero throughout the whole semi-axis, and all of a sudden it stops being zero in from the left of U equals 0. Okay, so that just cannot be analytic. Now, what we're going to do is we're going to do a combination of these modes such that the result is analytic. This looks like a crazy combination, but now we're going to show that in fact this satisfies the properties of analytic and bounded in the lower U and V planes. And some normalization constant which we will determine later on. Okay, so what are the values of this? What's this equal to? Well, this is minus alpha u I k bar alpha for u negative, and so we're considering things in the RU wedges. So this is on the left wedge, so that's, sorry, u negative being in the R union L wedge. U negative means we're in the right wedge, where this guy is equal to 0, so this is just equal to 0 when U is negative. Similarly, when U is positive, this guy is 0, and this is exponential of minus pi k bar alpha, alpha U pi k bar alpha. So let's operate a little bit with this. So just multiply and divide it by this.
Yeah. But C psi L.
Fine.
Okay, so it's for minus k.
Yeah.
So that because the k itself is for